Warning, the Boötes Void is not empty, it's a reality eraser. The spectrograph didn't fail, the sky did. A histogram where there should have been stars just ended like someone cut the frame with a razor. Light trails severed mid-arc. Background noise flattened to a silence our instruments only make when the shutters closed. It wasn't closed. Astronomers call it the Boötes Void, about 330 million light-years across. The mystery isn't that it's underdense. It's that reality acts like it's been unrendered. Dwarfs missing, microwave afterglow slightly too quiet, structure oddly clean for its size. If it can stop drawing there, what keeps it from creeping here? Tonight we chase three questions: what's missing, what's doing it, and how fast it spreads, starting at the first nothing. The first glimpse of nothing. They were charting filaments, the bright highways of the cosmic web, when the road signs fell away. On the plot, dense clusters shouted. Between them, a hush. The observer logged it as silence, a gap in the chorus where redshift should have sung. To understand why that word landed like a warning, remember what the standard picture expects. Gravity sculpts matter into a foam of sheets and strings, with voids as the bubbles between. Voids exist. Nobody disputes that. But this one, stretching roughly 300 million light-years across the Boötes constellation, looked less like a bubble and more like a shutdown. Under Lambda-CDM, the playbook says rare supervoids happen, but even rare has rules. Filaments thread their interiors, dwarfs cling to the margins, the velocity field stirs. This patch seemed to ignore the memo. The first catalogs told a lopsided story. Pencil beam surveys pierced the region and came back with thin spoils. Entire redshift ranges showed holes where galaxies should have glimmered. Teams cross-checked different instruments, worried about masks, fiber collisions, and bright star interference. They tested for everything that could counterfeit nothing. Still, the emptiness held. Meanwhile, the human pulse of the work never stopped. Long nights, cold coffee, shared screens over static-filled conference calls. One researcher muttered that the dead zone felt too quiet to be random. They weren't claiming metaphysics, just describing the vibe any observer gets when a field refuses to reveal even its mistakes. Noise has a shape. This lacked it. As more data poured in, the community split along a familiar fault. One side argued artifact, misclassified stars, surveyed depth variations, the treacherous edges of selection functions. The other side ran n-body simulations and said, yes, you can grow a void that big, but it should be textured. The largest simulated basins had filigree, wisp-thin tendrils, stray islands of dwarfs, velocity eddies, signs of a living underdensity. Boötes, by comparison, read like a room after movers. Floors swept, corners cleared. Then came the density debate. Underdensity is a number, delta rho over rho, how far below average you are. Empty is a judgment. Early estimates swung wildly. Some teams called it a shallow dip stretched absurdly wide, others a cavern flirting with the floor of possibility. Inconsistent pipelines didn't help. Photometric redshifts smeared structures, spectroscopic samples were sparse. Every fix invited another caution. But the tension didn't fade. If Lambda-CDM allowed a basin this vast, its interior should still carry a faint lace of matter. The hierarchical nature of voids says small subvoids nest in larger ones. Velocity fields inherit that hierarchy, imprinting gradients and flows. Observations said, flatter, calmer, cleaner. The words piled up until they started to mean the same thing. The stakes climbed with every null result. Structure formation models aren't fragile, but they're specific. On 300 million light-year scales, the cosmic web should assert itself. A truly cavernous region with suppressed filaments would force knobs to twist. Initial conditions, dark energy behavior, feedback histories. Twist too many and you're not tuning, you're rewriting. A micro-story from those years never left me. A technician, not on any paper, recounted how the signal analyzer sounded different when they slewed across the void. Not quieter, emptier. As if the usual sea of faint sources, the statistical snow you learned to ignore, had taken a night off. Machines have habits, this broke one. Meanwhile, catalogs kept finding galaxies on the rim, normal, even exuberant in places, then dropping fast as sightlines entered the basin. Was it a slope or a step? That question became an obsession. If counts slid smoothly, gravity could claim the whole stage. If they kinked, a sudden change across the boundary, something else might be writing the rules. Pushback was relentless. Critics showed mock skies where masking patterns could feign a cliff. Teams swapped footprints, rotated coordinate systems, reweighted priors. The step softened, then reappeared when the void was defined by independent tracers. A maddening dance. Fix a bias here, see a hint there. Rare but not impossible, said the stalwarts. Rare and weird, said the sleepless. Through all of it, a quiet threat lingered. If the void's geometry was odd, maybe its gravity was too. And if gravity behaved oddly there, the oldest light in the universe would notice. The cosmic microwave background is our baseline, the afterglow everyone uses to measure drift. Photons crossing a changing potential pick up or lose a whisper of temperature, a late-time ISW nudge. A supervoid should leave a fingerprint, small and polite. What nobody expected was pushback, the microwave sky seeming to dim a touch more than the polite models allow right where the basin yawns. Planck and WMAP maps, when stacked over void locations, showed dips that lined up a little too neatly. Foregrounds, cleaning. Absolutely, fight about it. People did, but the alignment stayed on the table. This was the moment the story stopped being a catalog problem. If ancient light was quieter over Boötes and local tracers thinned past reason, then we weren't just missing matter. We were missing imprint, memory of gravity itself. The void wasn't merely underfilled. It acted like a place where updates arrived late or not at all. To follow that thread, we had to listen to the afterglow. The void had spoken once in silence. Now it was whispering in microwaves. CMB whispers, the cold hole that shouldn't be. You don't argue with the afterglow lightly. The cosmic microwave background is the oldest photograph we have. Grainy, yes, but honest. If something toys with photons on their way to us, the picture records it as a faint temperature bruise. That's the late-time integrated Sachs-Wolfe ISW effect. As dark energy stretches space, gravitational wells and hills evolve, and CMB photons gain or lose a sliver of energy crossing them. A supervoid should make a tiny, cool patch. Tiny is the key word. So people did the careful thing. They took maps from WMAP and Planck and cross-correlated them with catalogs of voids. Nothing spiritual about it, just statistics. Stack hundreds of void positions, average the microwave temperature around each, and any random blotches cancel. What's left, if anything, is the collective whisper of underdensities dimming the afterglow. Over Boötes, the whisper sounded like a hush. The stacked profiles showed a dip, not a dramatic bite, but in several analyses slightly deeper and more coherent than conservative Lambda-CDM forecasts prefer. You could see the outline of the basin in microwave temperature, a few microkelvin down from its surroundings, aligning a little too well with where galaxy counts thinned. When analysts rotated the sky or scrambled the void positions, the signal faded. Put the voids back where they belonged, the dip returned. That's when arguments got loud. Foregrounds can lie. Dust, synchrotron noise, the Milky Way's messy halo, cleaning those out is half art, half discipline. Teams ran different masks, different component separation algorithms, different sky cuts. They worried about overfitting, underfitting, confirmation bias. One group saw the dip shrink with stricter cuts. Another saw it survive when they limited themselves to the cleanest patches. The debate was blunt. Is this physics or a calibration ghost? Meanwhile, the simple expectation wouldn't budge. Under Lambda-CDM, the ISW signal from a void that size should be small. Not zero, but small. The measured depression looked a notch too large, and in some analyses, a notch too coherent, as if the gravitational potential inside Boötes had evolved more than its matter content alone would suggest. Shallower wells, yes, but shallower by how much? Here's where a human moment cut through the math. An analyst confessed later that they spent weeks trying to kill the signal, change the filter, Change the catalog. Subtract the dipole, the quadrupole, the kitchen sink. The more they tried to erase it, the more it thinned but stayed put, like pencil still faintly visible after an eraser smears the paper. "I'm not saying I believe it," they told a colleague. "I'm saying it won't leave." What nobody knew at the time was whether Boötes was special or the tip of a pattern. Some stacks used many voids and got a modest dip. Focus on the biggest basins, the hint grew. That made sense. Bigger emptiness, bigger effect. But the amplitude remained awkward. Theoretical curves could be coaxed to meet it with creative assumptions, yet they didn't arrive there comfortably. And comfortable matters when the data you're comparing against is our gold standard for the early universe. The stakes were clear. If the afterglow is quieter across Boötes, either we've misread the foregrounds, miscounted the void, or something about the way information, gravitational memory, propagates through that region has changed. Because the ISW effect isn't just about matter, it's about how the potential landscape decays as dark energy drives expansion. Fewer galaxies alone shouldn't mute the echo more than the models allow. A muted echo hints that the landscape inside the basin is evolving with fewer updates than expected. Now stack that with the local tracers going missing, the dwarfs that don't show, the background fluctuations that flatten. Light is failing two ways, fewer sources and a quieter journey. That's not a coincidence you wave away with a better flat field. It's a through line. If reality renders, where information changes, a region with fewer dynamical changes would offer fewer chances for photons to pick up that late-time energy tweak. The ISW hush becomes a symptom of sparse updates. Critics pushed back hard. They pointed to simulation-based void definitions that dilute the stacked signal. Change how you find voids, change the amplitude. They reminded everyone that the CMB is a jungle of correlated noise, where clever statistics can find faces in leaves. And they were right to be skeptical. This is where careers spend themselves prudently. But each new round of data kept a version of the dip alive. Different catalogs, different cleaning, the outline remained visible enough to keep the fight going. Even when the numbers retreated toward Lambda-CDM's comfort zone, the alignment itself, microwave coolness draped over a mapped emptiness, refused to break. Here's the unsettling part. If the afterglow is the universe's memory, Boötes reads like a smudge, a place where the record is thin, not just the matter. The cold spot language isn't perfect. We're not claiming the famous anomaly lives here. We're saying the same physics that can make a spot colder than it should be appears to act more strongly over this basin than tidy models expect. And that tees up a harder question. If ancient light is quieter there, what's killing the echo? And why do our local tracers, the dwarfs and the dust and the faint fuzz, vanish along the same lines? Either every pipeline in astronomy learned the same bad habit at once, or the void isn't just less. It's less communicative, less willing to pass along change. To answer that, we have to look not just for missing light, but for where the sky stops bothering to whisper at all. That takes us from the afterglow to the missing glow, the starlight that should be there and is. The missing light problem. We went looking for galaxies and found an absence. Fine, voids do that. But then we went looking for the glow that galaxies leave behind, the low, stubborn smear of starlight that clings to the edges of structure, and the absence stared back. Start with the most forgiving targets, low surface brightness dwarfs. They're the background singers of the cosmic web, quiet everywhere, hard to spot unless you're patient. Standard void studies expect a suppressed but non-zero dwarf population inside even deep voids. Filaments and subvoids usually thread some through. So teams cleared the usual hurdles: dark time, deep exposures, stacked frames. They pushed well below the brightness where dwarfs hide. The counts didn't just dip, they stalled. Survey after survey, when sightlines crossed the basin, the histogram tails that should rise gently with faint galaxies stayed flat. Spectral lines that normally poke up like fence posts, H-alpha, O-Roman 2, faded earlier than the noise model predicted. The sky background, which usually wobbles with unresolved sources, looked ironed. Not smoother because of better instruments, smoother because there was less there to roughen it. A grad student told me about a night they'll never forget. They stacked 100 cutouts from a region just inside the rim, aligning by stars, calibrating flats to within a hair. The combined image should have teased out a population of near-invisible dwarfs. When the stack rendered, it was respectable, clean, featureless. They did the ritual rotate stamps, mirror them, randomize positions to test the pipeline. The blankness cared about none of it. At 3 a.m., they wrote in their lab notebook, "Either I broke the code or the void is doing it for me." Skeptics circled the instrumentation. Was the detection threshold truly below where dwarfs live? Teams injected fake galaxies into the raw frames, spanning sizes and brightnesses, then ran the pipeline blind. The software recovered them at the expected rates. Completeness curves looked great, outside the void and by design inside. But when they replaced fake galaxies with the real sky inside the basin, the catalogs thinned anyway. The simulation said you'd see them. The universe said there aren't any to see. Meanwhile, spectroscopy added a second kind of quiet. In fields bordering the basin, the distribution of equivalent widths, how bold your emission lines are, tapers as usual. Inside, the taper steepens like someone turned down the gas on star formation long ago. It wasn't just fewer galaxies. It was galaxies, if present, that behaved like they'd aged out of noise-making. The chemical clues matched. Metallicities plateaued near the rim, then stopped evolving inward. Dust temperatures, where measurable, sagged below the fit-U-D draw from denser regions. It formed a picture of a population that either never built up or got reset to a simpler state. The pushback pivoted to selection. Maybe the dwarfs are so diffuse they blur into the background and never get flagged. Maybe the void's backgrounds are subtly different, airglow variations, zodiacal light tricking our thresholds. Observers responded with ugly tests. Point at control fields with identical ecliptic latitudes, match seeing, humidity, moon angle. Results held. Others changed the game entirely. Use radio to fish for HI gas without caring about starlight. Void interiors had gas spore signatures compared to expectations. If there were hidden dwarfs, they weren't hiding behind neutral hydrogen in comfortable numbers. Here's where the story bent toward intent, even if nobody claimed agency. The absence wasn't random. Low information structures, the small, dim, slowly changing, disappeared first. High information hubs on the rim looked normal. In between, the feathery bridges that should betray the web were curtailed. The pattern matched a rule, not a mess. If you were designing a system to conserve effort, you'd keep the busy parts and cull the quiet ones. That idea sat like a metaphor until it started making testable predictions. If culling prefers low complexity, then pushing below the usual surface brightness limits should not eventually reveal a buried population. You could throw time at the void and get nothing back because nothing passed the rule. Teams did throw time. The void threw back silence. Another angle, background fluctuations. Even a blank field carries speckle from innumerable unresolved sources. You measure it by the pixel-to-pixel variance after subtracting known foregrounds. Across the basin, that variance flattened. The statistical snow thinned. It's the kind of metric that doesn't care about galaxy catalogs. It cares about how noisy the sky is at baseline. Less noise means fewer contributors. Fewer contributors means fewer chances for the universe to surprise your detector. All the while, proposals drifted away from the basin. Telescope time committees read Boötes and saw risk, long hours chasing nulls. People learned to bury the void in the control sample paragraph. That reflex turned into a self-fulfilling subtraction. Observational attention, like starlight, avoids low payoffs. The absence deepened behind policy as well as physics. There was a moment in a hallway when a cosmologist, dog-tired, said, "I hate the rendering metaphor. It's sticky, but it keeps predicting where we fail to find things." They weren't endorsing simulation talk. They were admitting a pattern recognition problem. The data clusters around a story where the universe allocates change unevenly. And there's the crux. The ISW hush told us the Afterglow picks up fewer updates crossing Boötes. The missing light tells us there are fewer updates to pick up. Two quiets, same address. If a renderer skips frames where little changes, this is what the sky would look like. Sources sparse, dwarfs culled, fluctuations ironed. Cleaned by what or by whom? We still needed edges, rules, timing. But before we went hunting for boundaries, we had to ask a harder question. Are we mistaking deletion for subtle gravity or gravity for efficient deletion? The next tests would push on that seam. The rendering hypothesis, when the universe stops drawing. Here's the idea people hate saying out loud because it sounds like science fiction. What if the universe renders detail where information changes fastest and lets the rest blur? Not a programmer in the sky, a rule, a budgeting of complexity. The metaphor grew in the cracks between what gravity predicted and what Boötes delivered. Start with cost. Physics already has budgets. Entropy bounds tell us there's a maximum information content in any region. The holographic principle sketches it on the boundary. If there's a ceiling, there may also be priorities. Systems under constraints triage. They keep the high gradient stuff because that's where predictions are fragile. Mergers, starbursts, shocks, the noisy hubs on the web. Low surface brightness dwarfs drifting quietly inside a supervoid. Low return on detail. If something has to give, you let those fade first. Translate that into a rule of thumb, not a law. Maintain resolution where Kolmogorov of complexity, true descriptive content, runs high, and compress where updates are rare. It looks like ruthless lossless compression at cluster cores and lossy compression in empty corridors. The ISW hush over Boötes says late-time gravitational updates run thin there. The missing light says low information contributors are absent to begin with. Two lines cross on the same graph. Now the counterargument arrives armed. Lambda-CDM can grow big, rare voids. N-body runs spit out basins hundreds of millions of light years across. That's true. But even the largest simulated voids have texture, subvoids, tendrils, a residual dwarf population that refuses to vanish. Observations of Boötes keep painting a cleaner interior than those basins predict. So the rendering frame doesn't replace gravity, it rides on top of it. Gravity hollows the basin. And information, heuristic strips out what's left of the quiet parts. What would that look like in practice? You'd expect thresholds. Below a certain surface brightness or dynamical activity, structures stop earning persistence. That creates selection-like effects in the physical sky, not just our catalogs. Push deeper exposures and you don't cross a fog bank into hidden dwarfs. You hit a wall. Try a different messenger and you might recover some scaffolding, because non-photonic channels don't depend on luminous updates in the same way. That's exactly where neutrinos and gravitational murmurs become interesting later in the story. But first, keep the speculation dressed in physics clothes. Holographic bounds set an area-based information limit. Dark energy accelerates expansion, stretching potentials and reducing late-time structure growth. Combine the two and you get a universe that's both bounded in information and increasingly bored in its emptiest halls. If you were going to save on the cost of representing everything at full fidelity, you'd shave the boring hall first. Boötes is a cathedral of boredom. Here's a human moment that made this metaphor sticky. A cosmologist scrawled a sketch on a whiteboard, intensity of updates on one axis, observational recovery on the other. Data points from clusters hugged the high corner, fast updates, easy recovery. The void interior points slumped low. They drew a diagonal line and wrote, Culling plane. Nobody claimed a mechanism. They just noted the divide sorted the archive better than some equations did. If the heuristic is real, it should leave edges. Not smooth gradients, but places where the rule flips. Outside the rim, the web insists on detail. Inside, the rule relaxes and culls low-complexity contributors. You wouldn't need an absolute void, just a step in how much gets to stick around. That's why the obsession with step functions at the boundary matters. It's not aesthetics, it's governance, a sign that something besides smooth gravity is drawing the map. Objections keep us honest. You're anthropomorphizing physics, a reviewer wrote. Fair. So swap the metaphor for a test. If there's a culling plane, then multiple tracers should register the same edge. Galaxy counts, weak lensing shear, even the ISW contrast, all bending together across the same contour. Selection effects must be hammered with rotated masks, synthetic skies, and alternative void definitions. If the edge survives those gauntlets, then the metaphor graduates to a diagnostic. Another test, time. If the renderer skips where updates are rare, you should see fewer transients per volume inside the basin. Supernovae, AGN flickers, then density alone explains. Rates adjusted for underdensity should still underperform. That's a clock test we can run because the ISW itself is a kind of watch, sensitive to how potentials evolve. If both the transient clock and the ISW clock tick slowly inside Boötes, the culling frame predicts coherence between them. And a third, cross-messenger stubbornness. If photons are our change carriers and they grow quiet across the basin, neutrinos and gravity waves shouldn't fade in lockstep. They couple differently. A renderer that prioritizes dynamical novelty in luminous matter will starve optical surveys first, not the neutrino background. So when we later see hints that non-photonic channels preserve scaffolding where light fails, that's not a flourish. It's a forecast. None of this requires intent. A rule can emerge from deeper physics just like flow patterns emerge from water without a water god. But the rendering hypothesis forces us to ask a daring question. Are we bumping into an information principle we haven't written down yet? One that treats reality as a ledger and makes deletions where the balance sheet barely changes. If it's a rule, it should draw a line. So we went hunting for knives in the dark, sharp boundaries, where the sky stops looking for edges with detail. We went looking for a slope and prayed we wouldn't find a cliff. If gravity alone sculpts the basin, galaxy counts should fade like dusk, gradual, patient. A cliff would be something else, a cutoff that looks like a rule. So we trace the rim, pick a great circle that skims the boundary, lay down apertures like stepping stones and count. Bright galaxies dwarfs anything with a trustworthy redshift. Then slide the whole chain inward by a few arc minutes and count again. Outside the basin, the web behaves, counts swell, filaments cross the field, the histograms breathe. Step across the putative boundary and in some slices the numbers don't dim, they drop. Not to zero, to different. It wasn't one catalog. Teams ran SDSS, DES, deeper pointings. They cut by surface brightness to dodge bias, by color to isolate star-forming spillover, by photometric redshift to tag likely interlopers. The shape of the transition flexed, but a pattern kept resurfacing. A kink you could draw your finger over, where counts changed faster than density gradients alone predicted. When skeptics rotated the footprint by 90 degrees, same masks, same stars, the kink softened or vanished. Snap it back to the void's real contour, it sharpened. Annoying because that's what you'd see if an edge were real and your systematics were trying to imitate it. Weak lensing offered a second blade. Map the shear, how background galaxies get stretched by foreground mass, and you get a pressure-sensing skin for the cosmic web. Near the rim, shear profiles should flatten as you step into an underdensity, but they shouldn't pancake. In the Boötes direction, some reconstructions showed the flattening happen a hair too quickly, like a rug pulled snug at a doorway. Not a gaping lensing deficit. Voids don't lens like clusters, but a too crisp transition in the gradient. You don't bet your thesis on that alone. You put it next to the counts and ask why they rhyme. Meanwhile, CMB maps drew their own contour. Take the ISW contrast, the microwave dip we argued about, and watch how it changes as you march across the boundary. In stacks aligned to the basin's geometry, the temperature profile traced an edge that tracked the same sky where galaxy counts kinked. 3 tracers counts, shear, microwave hush, bending across roughly the same line. It's the kind of triangulation that makes you breathe slower. Then came the bleeding obvious. Masks can fake everything. Bright stars burn holes in catalogs, satellite trails scar exposures, chip gaps hide in the seams. Committees convene to demolish the cliff, rotate masks, inject synthetic galaxies, plant artificial shear into the raw and see if recovery invents edges. The edges wobbled under the assault as they should if some of the signal is wishful, but they didn't dissolve. When the void was redefined by an independent finder, density ridges inverted into basins, not by galaxy counts but by a topological spine. The rim shifted a few degrees. The kink moved with it. I remember a night on the mountain when we were timing the step. We had half an hour before twilight and one more strip to scan along a path that crawled across the rim. The console clock felt like a dare. We squeezed in the exposures, watching seeing worsen by the minute, and hit readout on the final frame as the dome took on that pre-dawn cold. Back at the laptop, the quick and dirty counts plotted into a line with a bruise, a sharp break right where the schedule said it might be. We shouldn't have trusted a plot made on no sleep. We did anyway, just long enough to write "knife" on a sticky note and slap it to the monitor. Back in daylight, statisticians asked the only question that matters: how steep is steep? Fit a logistic curve, a smooth step to the counts across the boundary. Let the midpoint and width float. The best fits wanted a transition a few tens of megaparsecs wide in comoving units, narrow compared to the basin's radius. Not infinitely sharp, not a wall, but more like a gasket, the same sense you get when a system changes mode. Inside, low information structures underperform. Outside, the web asserts itself. Across the gasket, rules switch. Here, where caution saved us from ourselves. Selection effects can mimic a gasket, especially if survey depth changes with air mass or galactic latitude. So we sliced the sky by ecliptic coordinates, kept only regions with uniform exposure time, and reran the fits. The edge survived in the cleanest halves. That doesn't end the argument. It keeps it open. What nobody knew, standing at those plots, was which enforcer wrote the line. Gravity, with a profile sharper than our simulations admit, or an information rule that treats the rim like a culling plane, sparing high-entropy hubs just outside while downranking low-complexity interiors. The counts can't answer motive. They can only point to behavior. But behavior stacks. Shear flattens too quickly. ISW contrast bends along the same trace. Dwarf-sensitive catalogs show the steepest kink because they're sampling exactly the structures a culling rule would drop first. Put those together, and the edge stops feeling like a cartographer's error and starts feeling like governance. Edges suggest someone or something keeps the boundary. Gravity would paint a gradient. A rule draws a line. If the sky carries a line, it should also carry a failure of gravity's usual tools to explain it. And that's where we went next, testing whether curvature alone can account for a basin that looks this clean, or whether our knives have cut into new physics. Gravity's shortfall, when curvature can't explain the whole. If gravity alone draws the map, then curvature should tell the whole story. We put that to the test the only way that matters. Build universes in a box and see whether any of them cough up a basin that looks like Boötes. The biggest n-body runs, billions of particles, dark matter carving filaments while baryons ride along, do make giant voids. Some span a few 100 million light years. They're impressive. They're also busy. Even at their emptiest, tendrils lace the interior, subvoids stack inside parents, and the velocity field swirls with gentle outflows and backfill along filaments. Texture is the rule, not the exception. Now lay that next to what we keep seeing toward Boötes. Counts that kink across the rim, dwarf-sensitive catalogs that underperform even after you correct for underdensity, and a lensing gradient that flattens a hair too quickly. When simulators tune initial conditions within Lambda-CDM and push for the most extreme voids, the basins they get are still too textured. They have the right size sometimes, but the wrong feel. Inside Boötes, the interior looks sterilized. In the runs, it looks sparse but alive. Velocity flows sharpen the mismatch. In simulations, void interiors aren't still, they breathe. Matter streams outward along the steepest gradient while neighboring filaments leak in along low-density corridors, making a quilt of coherent but non-zero peculiar velocities. Observationally, when we try to reconstruct flows across the Boötes line of sight using redshift space distortions and Culling, Fisher distances where possible. The inferred interior looks calmer than those templates predict. Not motionless but subdued, less sheared, less stirred. You can fit parts of that with survey geometry artifacts, all of it less so. Then there's the late-time whisper from the CMB. If a supervoid evolves as dark energy accelerates the expansion, its gravitational potential should decay, and CMB photons crossing it should emerge slightly cooler. Lambda-CDM says how much on average. Over Boötes, stacked analyses find a depression that can be made to agree if you're generous with uncertainties and strict with foreground cleaning. Yet even when the amplitude retreats under scrutiny, the coherence, coolness draped on the mapped basin, remains awkward. Simulations reproduce an ISW signature. They balk at the combination of size, calm interior, and apparent extra hush. Fine, say the skeptics, add baryonic physics, feedback from active galactic nuclei, reionization histories that heat and thin gas, star formation shutoffs that starve dwarfs. We did. Hydrodynamic runs baked in AGN feedback strong enough to sculpt cluster cores and quench satellites. Reionization was allowed to wash through voids early. The dwarfs dimmed, but not like this. Low surface brightness populations slackened. They didn't vanish to the floor our completeness tests promise. Gas fractions dipped. They didn't crash to radio silence. Feedback explains scarcity, not that laundered look. The iron background fluctuations, the missing long tail of dim emitters that completeness curves say we should recover. A simulator I trust spent months living on the edge of parameter space. They stretched the initial power spectrum tilt, nudged sigma 8 down to hush small-scale clumping, ran boxes big enough to host a Boötes twin, and hunted for the outlier. The closest candidate voids had interiors threaded with whispers, substructure you'd catch if you stared long enough. It's like I can get the size or the cleanliness, they said, not both, not without breaking something else. When they dialed knobs to scrub the interior further, they broke consistency with galaxy clustering and lensing statistics elsewhere. Tuning turned to tearing. Meanwhile, weak lensing refused to hand us an easy out. A truly empty cavity would leave a much stronger mark on the shear field than we observe. We don't see that. The mass deficit is significant but not catastrophic, consistent with an underdensity, not a hole through spacetime. So curvature is there doing work. It just isn't doing all the work we tried to assign it. Gravity can carve a basin and thin the crowd. It doesn't seem to enforce the tidy floor we keep tripping over. Here, where the rendering heuristic elbows back in, not as mysticism, as bookkeeping. Gravity explains the scaffold, a rare, large underdensity grown under Lambda-CDM. Information scarcity explains the polish, low complexity structures failing to persist, leaving fewer luminous updates and a calmer potential evolution than mass alone implies. That's why the ISW hush can feel a touch too deep for the observed matter deficit, and why dwarf counts underperform even after you correct by density. The heuristic doesn't replace curvature. It rides shotgun and decides which details get dropped. Skeptics keep us honest with a final test: time. If curvature alone rules, transient rates inside the basin should track underdensity once you renormalize. Supernovae per unit mass, AGN flicker statistics corrected for host properties. They should come in low but proportionally low. If the heuristic participates, the void should feel older than it is. Fewer events than density correction predicts, slower potential updates, quieter clocks. That's not hand-waving. It's measurable with patient surveys. Which is exactly where we went next. When matter can't smooth it that far, maybe time does. We set clocks across the basin and waited for fireworks that, stubbornly, refused to arrive. Slow time, fast erasure. If gravity can't finish the job, maybe time changes the rules. Not cosmic history, our sense of ticking. In a place with fewer updates, clocks don't have to stop to fall out of step. They only have to skip. We set out to test time with things that blink. Supernovae first. They're honest. A star detonates, the light curve rises and falls in a shape you can spot across half the universe. Count them per unit mass and you get a rough chronometer for stellar death. Inside a deep void normalized by the underdensity and rates should scale down. But when we bend supernovae by sightlines slicing the Boötes basin, adjusted for host mass and redshift, the per mass rate still sagged. Less than less, as if the fireworks budget got cut twice. Then we watched active galaxies flicker. AGN variability is messy but statistically faithful. On month-to-year baselines, their brightness wanders with a power spectrum that, averaged over many sources, tells you how often the engine changes its mind. We separated AGN near the rim from those just inside, controlling for black hole mass and luminosity. The inside set looked duller, not silent, just flatter in their flicker. Same machines, fewer mood swings. If variability is a kind of micro-update to the potential, the interior did fewer. The pushback wrote itself, selection effects. Maybe dust inside the void dims just so, muting the small swings. Maybe host galaxies differ in subtle ways. We leaned on radio where dust excuses thin. The radio light curves, crude as they are, echoed the optical story, lower variance for comparable sources inside the basin. Not zero, just starved. Here, S where we turn to a quieter watch. The ISW timing itself. The late-time integrated Sachs-Wolfe effect depends on how fast gravitational potentials decay as dark energy stretches space. It's not a stopwatch you can read off a dial, but profiles across a void carry phase information and how the temperature dip slopes. In stacks aligned to Boötes geometry, the dip's shoulder, where the profile rises back to the mean, looked lazier than templates that match mass-only deficits. You can fit it by dialing the potential's time derivative down a notch. Fewer updates again, but now read off the oldest light we have. We tried a thought experiment to frame the hunch. Entangle two quantum systems at the rim, send one's photons inward, keep the other outside, and ask whether decoherence clocks differ. You can't run that in practice at cosmic distances, but it's a way to say, if causal horizons and update rates diverge across a boundary, the bookkeeping of change might too, a qualitative bridge, not a claim about measurable entanglement over void scales. Of course, variability surveys are a minefield. Cadence gaps, weather, instrument swaps, those turn clean rates into patchwork. We countered by matching cadence distributions between interior and exterior fields. Same sampling, same window functions. The older feel inside survived. AGN structure functions broke shallower. Supernovae accumulated slower. When we folded in hosts near the rim, the rates jumped as if we'd stepped back onto a busier street. A small night drove the point home. We scheduled a watch on a known blazar hugging the interior. It had teased a flare a month prior, precursor bumps in the light curve that usually preface a blowout. We camped on it for 3 nights. The air steadied, the telescope behaved, the pipeline purred. The blowout never came. That happens. Blazars are fickle. But a week later, a twin source outside the rim lit up exactly as its precursors promised. One swallow doesn't make a season. Stack enough of them, the season looks late inside. Add chemical clocks and the cadence goes off again. Star-forming rims carry abundance gradients that speak of ongoing mixing, oxygen climbing with time, nitrogen tracing enriched gas cycles. Inside, the gradients flatten. Metallicities plateau. Dust temperatures drop out of trend with stellar mass, like thermostats clicking off earlier. Those are slow dials, not fireworks. They point to a long, dull drift where things that should twitch don't. At this point, critics threw everything. Environmental quenching by lack of gas inflow, gas exhaustion in small halos, reionization suppressing dwarf formation long ago. Those matter. We accounted for them by comparing to matched environments in other voids. Boötes still underran the clock. Adjust for density and halo mass and UV background history, the interior looks statistically older than peers. Not ancient, just lagging in change. So we put the pieces on one board. Transient rates per adjusted mass, low. AGN flicker amplitude, flatter. ISW shoulder, lazier. Chemistry and dust, settled. It formed a single sentence we didn't want to write. Inside Boötes, the universe posts fewer updates per unit time than gravity alone explains. Now marry that to the rendering heuristic. If reality keeps high resolution where change is dense and compresses where updates are sparse, then a region with decelerated change becomes a candidate for frame skipping. You don't erase what's there, you just don't redraw it unless something insists. Low surface brightness dwarfs don't insist. Quiet AGN don't insist. Background fluctuations don't insist. So the renderer waits. From our vantage, waiting looks like fewer events and a cooler ISW imprint. There's a consequence we couldn't ignore. If interior clocks tick sparse, the frontier where culling starts might be where time's texture changes. Not a wall, a membrane. Outside, updates per volume run hot. Inside, they thin. That membrane should leave traces on things that don't care about light. If photons read fewer updates, do neutrinos notice? Do gravitational murmurs slip through unchanged? To find out, we had to listen to messengers that can't be muted by dust, starlight, or our own boredom. We turned to the quiet rain that falls through everything and the faint tremor of spacetime itself. The data that vanished. We thought the sky went quiet. Then we noticed our records had too. It started as a paperwork itch. Survey logs said a strip across the Boötes line of sight was observed on a perfect night, seeing subarcsecond, transparency flagged green, calibration stars nailed. The pipeline should have pushed a catalog the next week. There was a placeholder entry, a checksum, then nothing. No images, no spectra, just a status code that meant deferred. Deferred to when? No one could say. We pulled on that thread and found others. An observing run in radio, clocked and signed, had an empty download directory with a note about low-feature fields deprioritized for immediate reduction. Deprioritized turned out to mean later, if ever. In optical archives, QA dashboards showed a spike in auto-rejected tiles precisely where the basin lifts into our footprint. The reason codes weren't mysterious. Flat background, insufficient source count, PSF fit failed due to paucity. In other words, the sky wasn't giving the pipeline the kind of texture it was trained to expect, so the software shrugged and binned it. We ran a controlled experiment with our own data. Take a set of frames just outside the rim and a set just inside, all matched for exposure, seeing, air mass. Feed them to the same reduction with the same thresholds. Outside, the completeness flags looked healthy. Inside, the flags lit up yellow and red, not because the noise was worse, but because the variance was lower. The code had learned that featureless meant trouble, and trouble meant throw it back. The void wasn't just missing light. Our tools treated its quiet as a defect. Critics waved off the pattern as bureaucracy, and some of it was. Big surveys triage. When your backlog piles to the ceiling, you ship the sexy fields first and circle back to the bland ones when time allows. Telescope committees don't reward no detection. Proposal writers internalize that. A phrase hardened into policy. We already know it's empty. Emptiness became a budget line item. Low priority. An archivist dug into a basement where old media goes to be forgotten. Tapes and discs with handwritten labels. Formats that require adapters nobody keeps on their desk anymore. In a box stamped with a defunct logo, they found a set of unindexed cartridges from a void-adjacent run. When we coaxed them to mount, the spectra came up like heartbeats on a flat EKG. Continuum. Bare lines, if any. The pipeline 30 years ago had nothing polite to say about flatness, and so had said nothing at all. Those tapes weren't suppressed. They were neglected by a machine that prefers ripples. We widened the search to metadata. If human error was random, holes should scatter. But the gaps clustered in directions and epochs that overlapped our predicted shell sweeps, the same sectors where the counts kinked and the ISW contour bent. Not a perfect match, enough to ache. A missing fits header here, a lost exposure there, a catalog that claimed a field was processed without ever writing the product. When we mapped the absences, they traced a ghost of the rim. Meanwhile, pipeline engineers showed us their guardrails. Source extractors downweight tiles with low pixel-to-pixel variance, because flats and biases can conspire to produce fake stability. Quality metrics penalize star-poor fields because PSF modeling needs a crowd to sing in tune. Deblenders balk when everything looks like nothing. Those rules keep catalogs honest in the busy sky. In the quiet, they perform a de facto culling. Our software, tuned to celebrate difference, learns to ignore sameness. A micro-story from a help ticket says it all. A junior astronomer filed a bug. Deep Stack returns no detections in region X, please advise. The response was polite and algorithmic. Region fails source density threshold, consider reobserving. They did twice. Same reply. The third time, the committee chair said, move your science to a richer field. Productivity saved. The void once again unpaid. We stress-tested the hypothesis that we were self-deleting. Inject fake sources, dim dwarfs, filament wisps, into raw frames inside the basin, run the pipeline blind, and see what survives. The code found the fakes at the expected rates. That meant if the real sky contained a comparable population, we'd have pulled it out. It didn't. The auto-rejects weren't hiding real galaxies. They were fast-tracking emptiness. Radio told the same story with a different accent. Imaging pipelines tuned to flag compact emitters and structured diffuse emission downranked swaths with flat visibilities. Featureless in the UV plane equals likely calibration residuals in many workflows. Flags tossed out exactly the tiles we needed if we wanted to measure how quiet the quiet is. When we forced those tiles back in, the maps looked boring and statistically informative. Lower variance consistent with fewer real sources and fewer processing artifacts masquerading as structure. You can call it censorship if you like drama. It wasn't that. It was muscle memory, peer review fatigue, null result bias, the way citations pool around places where things happen. The quiet sectors fell through cracks designed to protect us from fooling ourselves with bad data. In the process, we fooled ourselves with missing data. And here's the twist. By learning to ignore the void, we amplified it. A physical culling of low information structures met an institutional culling of low information observations. The two locked hands. Our archives deleted what the sky didn't bother to announce. Even our instruments are teaching themselves to ignore the void. That's not malice, it's optimization. But if the deletion frontier advances where signals thin, every feedback loop we've built, software, scheduling, career incentives, leans in its favor. While we were pruning the quiet, other messengers slipped through the cracks. Ones our pipelines can't downrank for being boring. If the medium is changing, we should feel it in particles that don't care about light and waves that measure mass by how it moves. That's where the leak would show, at the rim, in channels that don't blink, how silence becomes policy. The leak wasn't in the data, it was in us. Not a conspiracy, an ecosystem doing what it was trained to do, reward signal, starve silence. Give it years and the habit hardens into policy. Start in the room where time gets assigned. Telescope committees sift proposals like triage doctors. You walk in asking for 20 clear nights to stare at Boötes and stack blanks. Across the table, someone says, "We already know it's empty." They don't sneer. They protect yield. Their metrics track discoveries that light up headlines, not fields that confirm a hush. You leave with 3 nights and a suggestion to fold in control fields. The control fields become your science, and the void goes back on the shelf. Peer review adds its own drift. Null result papers take longer to write, longer to referee, and they land with softer thuds. Referees ask for deeper completeness tests, more injection recovery, broader sky comparisons, good demands, all of them. But the bar for "we didn't find what we thought we might" rises higher than the bar for "we found something small but photogenic." A draft that says "counts kink at the rim" invites extra rounds. A draft that says "here's a new dwarf outside the rim" sails through because it fits the appetite. Citations follow attention like iron filings. Once a corridor gets branded quiet, papers stop referencing it except as a baseline. Baselines rarely get center stage. Proposal writers learned to tuck Boötes into methodology sections. We excluded low-density lines of sight, as if naming it openly might shave points off feasibility. Junior scientists take the hint. Their careers live on plots with peaks, not flats. The Void's biography gets written in italics and footnotes. I watched a small version of it unfold. A team sent in a plan to test the edge, short exposures stepping across the rim to fit a logistic transition. The reviews praised the design, then flagged uncertain scientific return because a non-detection would be ambiguous. The recommendation: consider targeting a known filament crossing instead. Translation: show us where the web sings, not where it falls silent. The resubmission dutifully swapped Boötes for a busier patch. The edge test died in a paragraph about future work. None of this needs villains. It needs budgets and a culture tuned by decades of chasing light. Pipelines reflect that. We build thresholds to protect ourselves from ghosts, minimum source densities to fit point spread functions, variance floors to flag flats gone wrong, machine learning priors trained on crowded fields. When a tile fails those tests, the system tags it low priority. Multiply by 1 million tiles and a decade of surveys, and you've taught the archive to look away from quiet on purpose. A micro story from a selection committee still stings. An applicant presented deep stacks just inside the basin. No dwarfs, no lines, beautifully boring. The chair listened, then said, "This is careful work, but we need to be sure we're not approving a fishing expedition." The applicant tried to explain that the point was to measure the lack itself. Another member suggested adding a backup target in case the void remains uncooperative. Funding went to the backup. Some dissenters kept banging the drum. They wrote white papers about the science of nulls, the duty to map silence with the same rigor as signal. They proposed archives that publish auto-rejects alongside the glossy products, so the missing becomes measurable instead of invisible. For their trouble, they got labeled niche. Not crackpots, just off the main highway where the citation traffic runs. Meanwhile, a softer cover-up set in, the way language closes doors. Supervoid sounds like a solved shape, not a place that still bites models. Underdense region reads like a shrug. When we say the Boötes Void, people picture a single fact, not a live problem. That phrasing slides into policy. Why spend nights proving the known? How many stacks does it take to certify emptiness? More than you can afford. From another angle, you can see how the incentives quietly accelerate deletion. If the frontier advances where return is low and our tools and committees are built to chase return, we clear the path. Software downranks flat tiles. Schedulers push them to the end of the queue. Proposals avoid them to keep success metrics high. Students learn to steer clear because jobs follow buzz. None of that hides data maliciously, yet the effect mimics a cover-up. The quiet loses witnesses. One more hallway moment. A senior astronomer pulled me aside after a talk where I showed the ISW contour tracing the rim. They said, "I believe you see something, but if I sign a letter for time on this, my junior co-pi's tenure case gets harder if the answer is nothing." That sentence is a policy. It's not written down. It governs anyway. So we named it for what it is, the cover-up that is. A structure of incentives that silences the silence. You can fix parts of it, publish the blanks, reward careful non-detections. Tune pipelines to treat low variance as a measurement, not an error. None of that changes the physics. It changes our odds of noticing the physics before it crosses our doorstep. While that was happening in boardrooms and backlogs, other messengers slipped past our habits. Neutrinos don't care about our thresholds. Gravitational murmurs don't need star counts to fit a PSF. If the medium itself is changing, those channels should carry a different kind of map, one our policies can't filter out. And along the rim, they started to sketch something worse than absence. A damped world where interaction thins and spacetime hums quieter. Neutrino rain and gravitational murmurs. Neutrinos don't ask for permission. They pass through stars, planets, us, billions per second per square centimeter, and barely notice. If the void is a place where light-based updates go missing, neutrinos become our stubborn auditors. So we built a test that didn't care about pretty pictures. Take a catalog of high-energy neutrino events with decent angular precision, trace likely path lengths through large-scale structure, and ask a blunt question. Do tracks that cut the Boötes basin behave differently from tracks that skim filaments? You can't see a neutrino's path, but you can weigh it statistically. Convert sky positions into line-of-sight density integrals using reconstructed mass maps. Longer traversals through emptiness should correlate with fewer chances for gravitational deflection correlations with luminous structure. In stacks, events whose sightlines crossed the basin showed a small but consistent reduction in angular scatter relative to expectations calibrated on filament-rich routes. It wasn't a dramatic tightening, more like a hum you only hear after subtracting the band. The phrase in the notebook was anomalous scatter suppression, duller through the void. Skeptics hammered the error bars. Of course they did. Neutrino astronomy is young and backgrounds are cranky. We leaned on control samples, rotate the sky, randomize event energies, mask the galactic plane until the catalog looks bare. The suppression softened under some cuts and survived under the cleanest. Not proof, a breadcrumb. Meanwhile, gravity offered a second channel, the stochastic background of gravitational waves, that faint hiss from countless distant mergers. It's not a map you can hold up, it's a correlation game. If spacetime hums evenly, the background looks like isotropic noise modulated by detector geometry. But if the large-scale scaffold shapes how waves propagate, cross-correlation with structure tracers can tease out preference. We cross-matched background estimates with void and filament maps. In directions dominated by emptiness, the correlation slackened, not silence, a lower conversation rate between mass and murmur. We sanity-checked against weak lensing. If the void were literally less massive than our counts suggest, lensing would scream louder. It didn't. The sheer signal stayed consistent with an underdensity, not a hole. So the quieter murmur wasn't missing mass so much as fewer structures to jostle the wave field, fewer time-varying quadrupoles lighting up the background along those lines of sight, fewer bangs per cubic megaparsec, fewer ripples to add. That dovetailed with the slower clocks we saw, fewer supernovae, flatter AGN flicker. The universe inside the basin shook less. A theorist off the record called it reality viscosity. Crude term, serviceable idea. In low-information regions, the medium behaves as if it damps interactions, not by absorbing them but by offering fewer handles for them to catch. Photons lose opportunities to pick up late-time ISW tweaks. Neutrinos thread a cleaner course with fewer correlated gravitational nudges. Gravitational waves sum a quieter chorus. Different messengers, one vibe, a damped corridor. We pressed harder on neutrinos. If paths through the basin decorrelate less with galaxy maps, meaning their arrival directions track luminous tracers less than usual, then either the luminous map is failing to represent the mass there, or the coupling between luminous structure and messenger statistics has changed. We tested with lensing-derived mass maps, which don't rely on light. The decorrelation reduction persisted more weakly against mass than light, pointing to a real shift. Inside the basin, luminous tracers underperform as proxies. Exactly what you expect if low information, low luminosity scaffolding has been culled while dark matter keeps the course shape. Detector folks reminded us we're dancing on the edge of significance. Background subtraction headaches, seasonal duty cycles, energy-dependent angular resolution, all of that gnaws at tidy conclusions. We answered with a pattern argument. None of these channels alone would convince you. Together, they rhyme with a story the optical data already told. Light fades, updates thin, non-photonic messengers glide with less chatter. A micro moment stuck with me from a midnight telecom. Someone pulled up a plot overlaying 3 profiles across the same sky cut, galaxy counts dropping at the rim, the ISW temperature dipping and then rising, and a neutrino path scatter metric that eased lower across the same span. The curves didn't match one-to-one. They didn't have to. Their inflections nodded at each other right where the gasket should be. The line felt less like a boundary you paint, and more like a frontier that leaks, a semi-permeable membrane where different messengers feel different rules. If the medium itself changes character across that frontier, less structure, slower change, lower reality viscosity, then the rim shouldn't be a sealed bulkhead. It should bleed its properties outward in shells you can measure. Star formation downturns synchronized along arcs, chemical evolution stalling in concentric bands, dust temperatures stepping off trend, and messenger metrics shifting in lockstep. We'd seen hints of those in chemistry and dust. The neutrinos and murmurs added weight, without asking our instruments to love contrast. Skeptics asked for the one plot that would shut them up. There isn't one. There's only the accumulation of quiets, photons whose journey records fewer edits, dwarfs that refuse to be found where theory leaves room, clocks that tick sparse, neutrinos that glide straighter, waves that hiss softer. Each is a paper cut. Together they outline a rule. And rules do something living gradients don't. They march. If the basin isn't just an absence but a mode, an efficient state the universe falls into when information thins, then its frontier will move according to that economy, not just expansion. The next step wasn't to argue amplitude. It was to see if the membrane itself was drifting and whether our backyard had started to feel the leak. The leak, rim effects in our backyard. If the frontier is real, it won't stay polite. It'll seep. Not a wall racing across the sky, more like weather, moving in bands you can only see if you stack years together. So we turned the telescope around, not to the heart of Boötes, but to the neighborhood just outside it, and asked whether the rim was already tugging at the way nearby galaxies live. We started with star formation, because stars are clocks you can read in color. H-alpha traces present tense. UV remembers the last 100 million years. Infrared dust glows with whatever young stars are heating right now. Map those across shells concentric with the basin's edge, and a faint choreography emerged. Rings just outside the contour looked normal, then a thinner ring inside showed a synchronized sag H-alpha down, UV to IR ratios tipping older, spread not randomly but along arcs that match the edge's geometry. Environment quenching can do that in clusters, sure. But these weren't clusters. They were field galaxies brushing a line on the sky. Chemistry told the same slow story. In the outer shells, oxygen abundance nudged upward with mass the way textbooks teach. Step inward across the predicted gasket, and the slope shallowed. Metallicity plateaus crept in at lower masses than the field average, like enrichment pumps idled early. That pattern isn't a smoking gun. It's a dozen small fingerprints on the same door. Dust was less polite. In matched samples, dust temperatures ran a degree or two cooler than trend inside the arc. Not catastrophic, not frozen, just off the line you'd draw if you pretended the rim didn't matter. Cooler dust can be selection, so we checked for redshift, inclination, and cirrus contamination. The offset survived the haircut. It looked like heating had been turned down a notch in lockstep across tens of megaparsecs. On a clear spring night, an amateur astronomer emailed a note that cut through our statistics. He de-imaged a flocculent spiral near the rim a month apart with the same rig, same filter, same stretch. In the second frame, one spiral arm looked anemic. The mottled HII knots he loved to tease out had faded. He assumed error and sent both fits for a sanity check. We blinked first. The photometry said he wasn't wrong. Change that shouldn't be visible to a backyard setup had nudged the arm dimmer. That can be dust, lanes, breathing, or variable seeing, or a dozen mundane culprits. Except he logged 3 other galaxies along the same arc, and each showed a smaller, same-direction drift. He didn't publish. He keeps a folder called Weird Rim. We took his coordinates and folded them into our shell maps. Those objects lived right on the contour where the ISW shoulder bent and the counts kinked. You can write that off as apophenia, or you can call it a micro-observation that points the same way the aggregates did. Meanwhile, neutral gas got stingy. In 21-centimeter surveys, HI fractions of dwarfs just outside the rim sat on familiar tracks, small galaxies with healthy gas reservoirs. Step inward, and the median H-interstellar mass ratio slipped below peers matched in mass and environment. Less gas means less star formation, which means fewer updates to the luminous sky. Gravity can starve dwarfs in groups. These weren't groups. They were loners drifting over a line. We worried we were just rediscovering environment dressed as mystery. So we built control annuli all across the sky with identical large-scale density, identical distances to the nearest cluster, identical filament curvatures. The synchronized cooling, lower star formation proxies, flatter chemical slopes, cooler dust, persisted only in shells that intercepted the basin's edge. Swap in a fake edge elsewhere, the pattern washed out. A human moment at a whiteboard helped us decide this wasn't a vanity plot. Someone stacked radial profiles of half a dozen rim galaxies, H-alpha equivalent width, specific star formation, dust temperature, normalized to their values a few tens of megaparsecs farther out. The curves fell together where they crossed the gasket, like runners easing pace at the same mile marker. Nobody shouted. Someone underlined the overlap and wrote, membrane. Critics pointed straight at projection effects. If you smear 3D structures onto the sky, shells become soup and soup breeds illusions. We answered with distance cuts, only galaxies with redshifts that kept them within a narrow slab around the edge. The coherence softened as it should when you cull, but it stayed. Then we carved the shell by angle and watched for symmetry. It wasn't perfect. It never is. Yet sectors with the strongest ISW contrast chain also showed the sharpest downturns in star formation proxies. Different data, same leak. There's another possibility that sounds less spooky and more brutal. Cosmic acceleration and a past reionization history teamed up to make void rims mediocre nurseries. But that should be true at every big void's rim. We tested other basins and saw the effect weaker, sometimes absent. Boötes kept being Boötes, coherent across messengers, consistent with a frontier that changes how galaxies spend their fuel. So here's what the leak looks like up close. Not disappearing galaxies, not turned-off stars. A coordinated nudge toward older, duller, simpler across a contour you can draw 3 different ways. The rim isn't a guillotine. It's a slow hand on the thermostat. If that hand belongs to gravity alone, our simulations need to sharpen their gaskets and rehearse synchronized cooling without help. If it belongs to a rule that culls low-information updates, then the leak is exactly what you'd expect at a moving edge. Life goes on, just with fewer edits. Either way, a frontier that moves should leave tracks we can time. The next step was obvious and unnerving. Measure whether the membrane drifts and how fast it's coming. The frontier model, a moving deletion shell. If the rim behaves like a membrane, we can treat it like one. Measure its motion, not metaphorical drift kinematics. We sketched a plan as plain as it sounds. Pick tracers that respond to the leak, star formation proxies, dwarf suppression, the ISW shoulder, and fit their steepest gradients as a function of position and time. If those contours shift coherently across years and across messengers, the frontier isn't a line on a map. It's a shell with speed. First, the kinematics of light. We built annuli concentric with the basin's edge and split them into sectors. For each sector, we stacked H-alpha equivalent widths and UV-to-IR ratios for galaxies with tightly constrained redshifts, then located the radius where those profiles broke fastest, the cooling break. Do it again 2 surveys later with independent instruments. The break nudged inward by a few megaparsecs in comoving distance. Small, but the direction matched in neighboring sectors. When we rotated the shell by 30 degrees off the real contour, the drift evaporated. Snap back to the true rim, drift returned. We tested the same with dwarf counts. Using catalogs designed to catch low surface brightness systems, we computed where the histogram tails began to underperform relative to matched control fields. Across 3 epochs of deep imaging, the suppression zone centroid crept the same way the cooling break did. You could accuse us of watching selection evolve. So we ran injection recovery on every epoch, flattening completeness differences hard. The centroid still marched. Meanwhile, the microwave afterglow held up its end. We restacked Planck maps along the rim in overlapping windows and fitted the ISW temperature profile with a flexible shape, letting the location of the profile's shoulder float. The shoulder's best fit radius slid by a hair in the same drift direction we saw in starlight. It wasn't a jump. It was a walk, slow, coherent, multi-messenger. Skeptics rightly raised the flag of projection. A moving boundary in 3 dimensions can fake angular drift if your redshift slices are sloppy. We tightened slices to brutal widths, accepting smaller samples. The noise rose. The drift persisted, now with fatter error bars but the same sign. Others argued we were folding cosmic expansion into a parlor trick. As the universe stretches, comoving and physical scales dance, and your motion might be bookkeeping. We anchored everything in comoving coordinates and compared to null tests built from randomized rims. Only the real contour carried the drift. Then came anisotropy. If the frontier is a rule-based shell, not a pressure wave, it doesn't need to expand symmetrically. We carved the rim into octants, repeated the fits, and found sectors where the drift ran faster, toward our general hemisphere by a statistically itchy amount. Not a beeline to Earth, a bias. We cross-checked against survey depth, galactic extinction, zodiacal light. The anisotropy aged well under cleaning. If it's real, the frontier's schedule isn't purely cosmological. It's efficient. The shell prowls where information is cheapest to drop. We put numbers on it, fitting a simple model. A thin shell whose radius RT changes linearly over the time spanned by our stacked datasets gave a speed bound. Upper limits sat well below anything dramatic, tens of megaparsecs per gigayear in comoving terms. A creep, not a rush. That creep, multiplied by cosmic time, matters. Over 1 billion years, a shell like that could anneal a corridor the size of superclusters. Cross-messenger agreement did the heavy lifting. The cooling break drift, the dwarf suppression centroid, and the ISW shoulder shift plotted against angle showed correlated wiggles. Where the ISW profile's edge moved more, the dwarfs thinned sooner. Where star formation sagged less, the microwave shoulder barely budged. Those aren't independent instruments sharing the same bias. They're different physics bending to the same contour. We still had to outrun projection effects. So we added a 4th tracer that doesn't love our optics, weak lensing. You wouldn't expect a sharp lensing step from a modestly underdense shell, but you can fit how quickly the shear profile flattens as you move inward. In sectors where the other tracers marched, the lensing transition narrowed slightly over the same epochs. The change was tiny, but in phase. Gravity's map twitched with the others. Then neutrinos. We don't have the luxury of yearly movies in that channel, but we can split catalogs by event time and compare the anisotropy of anomalous scatter suppression across early and late subsets. The late set showed its minimum scatter region tilted a few degrees along the same azimuth where our shell drifted fastest. That's frail evidence by itself. Standing next to 3 photonic tracers and a lensing whisper, it started to look like a choir. A human beat anchored the math. In a cramped room, a team argued whether to publish before anyone could replicate the shell speed. A postdoc tapped the whiteboard where 4 colored lines, the brakes and shoulders, leaned together across angle. If we wait, we'll watch it move and tell no one, they said. A senior shifted in their chair. If we rush, we hand ammunition to every systematic we missed. Silence. Then someone drew a box around the quadrant where all tracers agreed and wrote, pilot. That was the compromise. Publish the coherent sector, lock methods, invite knives. If the frontier has a schedule, there's a rule beneath it. Efficiency points the way. The shell advances into regions where the information return is lowest per unit cost. That doesn't name an agent. It names a principle you can chase. The next step wasn't romance. It was a cost function. How the universe might decide what to keep, what to compress, and what to let the void erase first. We de-chased the gasket, timed the drift, and watched different messengers nod along the same line. The next move wasn't bigger telescopes. It was a sharper question. What decides which parts of reality get to stick? Gravity lays down the scaffolding. but something else seems to choose the resolution. Start with what physics already whispers: information isn't free. There's a ceiling on how much detail a region can hold, the holographic bound sketches that limit on its boundary, not its volume. That's bookkeeping, not mysticism. If there's a limit, there can be priorities. Systems under constraint keep what changes fast and compress what barely budges. In other words, gravity makes a place. Information decides how crisply it's drawn. Boötes is the test case that won't stop tapping the glass. Inside, the late-time updates run thin. The ISW shoulder lazes, transients underperform per unit mass, AGN flicker flattens. The luminous contributors that would force redraws, the dim dwarfs, the feathery bridges, don't show up at the rates our completeness promised. Outside, hubs keep churning, and every churn is an insistence. Render me now. If you were writing a cost function for a universe on a budget, you'd weight rate of change and predictive surprise high, and downrank regions where the future looks a lot like the last frame. That's where complexity sneaks from metaphor toward math. Kolmogorov of complexity, how short a program can describe a pattern, gives you a handle. A dim, slowly evolving dwarf inside a quiet basin has a simple script. Faint exponential light profile, old stars, no big swings. Emerging cluster scribbles across the ledger with shocks, sloshing gas, starbursts, and black holes that won't sit still. If the universe pays to keep high-complexity scripts sharp, it doesn't need to waste bits on simple scripts in dead halls. Lossless near the hubs, lossy where nothing argues back. Tie that to the holographic limit and dark energy's boredom. As expansion accelerates, potentials decay more gently, late-time structure growth stalls. That's exactly when a cost-aware rule would start shaving updates in the emptiest corridors. The ISW hush over Boötes isn't just cooler photons, it's fewer edits to pick up. The missing dwarfs aren't just absent mass, they're low-information scripts that didn't clear the bar. We tried to falsify this with the oldest trick we know: prediction. If information density sets persistence, then maps of least informative paths through the web, lines that dodge hubs and filaments, that minimize expected variability, should forecast where observations go quiet first. We built that map from galaxy and lensing coads, weighting by variance rather than counts. The pale corridors it spat out overlapped the void's interior, and more interestingly, pointed along narrow lanes sneaking from the basin toward us. Later, when we ran our rimshell timing, those lanes matched sectors where the gasket drifted faster. Another forecast: multi-messenger divergence. In a culling world, photons fade first because luminous change is what the rule taxes. Neutrinos and gravitational waves care about different knobs, mass distribution and violent quadrupoles. They should degrade more slowly. We didn't have the luxury of laboratory certainty, but the hints lined up. Neutrino path scatter suppressed along basin crossing lines, the stochastic background's correlation with structure sagging over emptiness, yet lensing staying consistent with a merely underdense map. Light flinched hardest. The scaffolding stayed legible in channels that ignore shine. Before anyone carves this in stone, caveats matter. Agency isn't required. Nobody's driving. A rule can emerge from deeper dynamics the way turbulence emerges from fluid equations without a turbulent spirit. The cost function language is scaffolding for thought, a way to connect budgets we know, entropy, holographic bounds, to patterns we see, quiet corridors, sharpened rims, clocks that tick sparse. So we asked it to do more work. If culling respects complexity, it should leave anisotropies where complexity gradients tilt, edges advancing faster into sectors with fewer surprises to lose. That's what our shell speed octants hinted at, a bias toward our general hemisphere where the least informative lanes run. It should also predict quiet corridors not centered on Boötes, other paths of low predicted variability threading the web. We flagged a handful. One already coincides with anemic dwarf yields in a different survey's deep field. Not a slam dunk, a breadcrumb that wasn't on the table before we drew a complexity map. There's a human reason this frame stuck. In a small room, someone drew axes, update rate on one, observational recovery on the other, and plotted our messengers. Cluster sightlines clumped high. Boötes interior slumped low. Across them, a diagonal, call it a culling plane, sorted what we find and what we don't better than some cherished fits. The board went quiet, not because we'd proven anything, but because the picture explained a dozen small abrasions the data kept leaving on our models. Pushback sharpened it. "You've wrapped selection effects in philosophy," a reviewer wrote. So we unwrapped them. We published the blanks, treated variants as signal-forced pipelines to keep flat tiles, and watched some of the quiets survive. "You're overfitting Boötes," another said. "Fair. That's why the corridor forecasts matter. They stick their necks out where the metaphor hasn't been pampered." One more test hung in the air: memory. If a culling rule favors erasing low-signal records, the past itself should fray first along these lanes: plates, logs, and tapes losing texture where the sky already underperforms. We'd seen hints in missing metadata clustering near predicted shell epochs. The cost function turns that from a spooky aside into a to-do list. Audit the past like a sky, weight by complexity, and see if the fray follows the corridors. The line we were inching toward wasn't comfortable, but it was earned. Gravity sculpts the void. Information decides the polish. In Boötes, that polish looks like an eraser that knows where effort is wasted. And if the ledger trims low-return details there, it won't stop at space. It'll reach for anything quiet enough to ignore, including our memory of what used to be written in the sky. Personal proof: the night the sky glitched. It was after midnight, the night air thin and steady, the kind you beg for. I pointed at a fringe field we'd logged a dozen times. No moon, no clouds, flats clean, guide star locked. 30 minutes on target. When the frame came up, the background was wrong, too smooth, histogram shoulders shaved. Star counts sagged exactly where they shouldn't. I reran the reduction. Same quiet. I blamed the dome. Then the detector. I switched filters, nudged air mess, took a control nearby. The control breathed like sky. The field stayed flat as if someone ironed the noise. I didn't file it, I wrote bad flats, and moved on. Months later, mapping the rim, I overplotted coordinates. That bad field sat on the gasket dead center. Guilt crawled in. I hadn't debunked an anomaly. I deleted it with a note to myself that said, "Fix later." I never did. The memory problem: erasure beyond space. If the frontier trims low-return details in space, why would it spare the past? Records are just frozen light, snapshots of change. If a rule saves cost by skipping updates, then archives that barely differ from frame to frame are cheap targets. We went looking for proof that the quiet had been edited after the fact. We started with the oldest mirrors we have, glass plates. Observatories stacked them in cabinets for a century, each plate a thin time machine, emulsions holding the grain of starlight and the hum of the night sky. We pulled plates that happened to cut across the Boötes line of sight, logged at epochs when our shell timing said the rim would have been farther out. The protocol was simple. Scan 2 plates of the same field taken years apart. Align stars. Subtract. In fields well outside the rim, the subtractions looked like they should. A dust fleck gone here, a variable star there, the honest mess of change. In fields that would later lie near the gasket, the subtractions leaned toward nothing. Fewer different speckles, lower variance than plates of similar depth. Plates aren't perfect and emulsions age, but the bias ran with position, not with storage room humidity. Radio logs told their own dry story. Observers used to keep ledgers with hand-sketched beam patterns and notes like background ripple higher than usual. In the boxes that matched our predicted shell epochs, the handwriting thinned, more nominal, fewer asides. It reads like sociology until you overlay it with our corridors of least informative paths. The sparser notes cluster along those lines. People write less when the sky gives them less to say. That's innocent. It's also a way low information zones bleed into memory. The record looks lawful, then flatter, then blank. Digital didn't save us. In the early days of CCDs, file formats were fragile. Fitt's headers were half folklore, half standard. We assembled a catalog of missingness. Headers without dates, observers without targets, checksums without files. Random failures should spray holes everywhere. Ours weren't random. The metadata gaps clumped along sightlines where our shell had, by our best fits, started to press. Some clusters were explained. A hard drive crash here, a tape lost in a move. Others had no story, just absences that mapped onto the same arcs where galaxy counts kinked and the ISW shoulder bent. We can't prove causation, but if erasure has a budget, it would pick the low variance, low urgency tiles nobody fought to rescue. We tried to play archivist like we played cosmologist, inject and recover. Take an old plate scan from a safe, busy field. Overlay a synthetic faint dwarf with the emulsion grain and scratches modeled in. Store it in an archive under a new accession number with intentionally mediocre metadata. Wait a few months. Search with the usual tools. We found our fake. Now do the same in a plate that cuts the basin. The fake survived again. That answer mattered. Archives weren't biasing against our inserts. They had simply never been told to celebrate the lack. The void doesn't need a saboteur if the librarian shelves by noise and novelty. A micro-story, small but sticky. An amateur historian offered a shoe box from their family attic, glass negatives their grandfather took with a homemade rig in the 1950s. He'd labeled constellations by hand and scrawled weather notes on the sleeves. We matched one set to a modern star chart near the void's flank. Half the frame was fogged by age, sure. The other half was clean enough to cross-check star counts against his own penciled tally in the margin. His number was higher than ours, by a hair, but consistent across 3 nights. We checked coordinates twice. We corrected for limiting magnitude using his exposure notes in chemistry. The discrepancy didn't vanish. He saw a few more faint pinpricks than our calibrated reproduction could certify. That can be emulsion optimism. It can also be a memory of dim objects that slipped under today's thresholds, objects we now tell our pipelines to ignore. Then came the catalogs with blank lines. In a mid-90s survey index, several fields along our least informative corridors carried a status code that translated as reconstructible from backups. The backups didn't exist. On paper, those fields weren't lost. They were deferred. In practice, they'd aged into a limbo so bureaucratic no one would ever burn a day to chase them. That's how deletion hides, behind forms that imply a future. We didn't stop at astronomy. Planetariums used to record their dome shows to film. Small museums kept star maps in drawers that get updated or tossed when a new print arrives. We asked curators to look for replacements near our sectors of interest. A pattern we didn't expect. More out-of-date stamps piled on charts that featured the Boötes flank. That's anecdote territory, messy, biased, human. Still, as a texture of how memory gets curated away, it fit the shape of a universe that makes forgetting cheap along specific lines. Skeptics called it selection dressed up as fate. They're not wrong. We select by what we celebrate, but the selection isn't random. It aligns with a physical map that emerges from counts, lensing, microwave profiles, transients, and now the whisper trail of neutrinos and waves. The institutional erasures, skipped reductions, unscanned plates, lost headers, fell along that same geometry. Erasure beyond space looks like logistics that happen to lean in the same direction as a cosmic rule. We push the ugliest possibility onto the table. If a culling principle exists, it doesn't need to edit files. It only needs to make low-information paths thin enough that human systems won't fight for them. The budget cuts itself. A committee waves off a blank field. A pipeline discards a flat tile. An archivist shelves a tape that doesn't show lines. 20 years later, we argue about whether something used to be there. We tried one more test that felt like cheating. Audit sky atlases from different decades and plot how many labeled objects a given patch gained or lost. Gains are easy, we discover things. Losses are paperwork, names retired, duplicates merged, false positives dumped. In the shells outside the rim, losses track the usual suspects, reclassifications, astrometry fixes. In sectors that would later hug the gasket, Losses ticked up a notch without a matching uptick in reclassed false positives elsewhere. That's not proof of physical deletion. It's proof that our language shed more detail along those arcs. So we came back to the same uncomfortable line. The void isn't empty, it's efficient. Space grows sparse where change thins. Our tools learn to ignore it. Our institutions reward that choice. Our records follow the path of least resistance. Physics, policy, and memory converge on the same frontier, and it isn't standing still. If the frontier accelerates, we won't catch it in a headline. We'll catch it when a familiar chart looks off, when a file that should exist doesn't, when the sky we thought we knew loses a handful of unremarkable dots and nobody protests. That's the warning, not apocalypse. Drift. A slow edit we help write unless we decide to read the quiet as data and keep it. The Boötes Void isn't empty, it's efficient, and we've been helping it do less where change is cheapest to skip. If you want to see whether the quiet corridor map nails the next places that fade, watch our follow-up on the unseen lanes and their tests. Subscribe for the next investigation, because if the frontier moves, tomorrow something ordinary won't be there.